Today we're going to talk about ionic bonding. We just learned about ions and how ions form and why ions form, and now we're going to find out how that translates into compounds. How it works is, quite often it's possible for two elements to get close together or meet each other that have the ability to satisfy each other's needs for stability. Remember, some elements, typically metals, need to lose electrons to become stable, and some other elements, typically nonmetals, need to gain electrons to become stable. So that's a sort of a nice match that can often occur when the right elements get together. For example, imagine that you had a group 1 element, like sodium for example. What it needs to do to become stable is to become a +1 ion by losing 1 electron. A group 7, on the other hand, needs to gain 1 electron, like chlorine for example, to become stable. So a natural thing to occur would be that the one that needs to lose an electron, the group 1, would give that electron to the atom that needs to gain an electron. And when that occurs, I now have 2 ions. Let's use sodium and chlorine as real-life examples. Chlorine needs to gain an electron. There's an open spot right there. Sodium needs to get rid of its electron, because remember, 8 dots is stable and no dots is stable. So the natural thing to occur here would be that the dot from sodium will transfer over to chlorine. Now what you've got is 2 ions, and they're oppositely charged. Well, oppositely charged things attract each other, and right now there's energy stored in the position of where they are because they're attractive to each other and they're held apart. It's kind of like holding 2 magnets apart. You store energy in the position where they are. You let them go and the energy comes back as motion. So as soon as you let these 2 ions begin to move, the oppositely charged particles will attract to each other. And now you have a compound, an ionic compound. Sodium chloride is the name of it. These ions are going to stack together in a way that will minimize how much energy is stored in their positions. Of course, you won't have just 1 atom of each. You'll have a large collection of atoms, and this is sort of a little animation of what might happen as the compound forms. The positives and negatives are moving toward one another, and they make this little cluster. There won't be 2 of each either. There'll be a very large number, and so you'd end up with this regular pattern that gets these things as close to each other as they could possibly be to minimize how much energy is stored in their attractions. That arrangement is called a crystal, and of course real-life crystals are 3-dimensional because atoms aren't flat things, they're 3-dimensional. So this drawing here is actually what we imagine that a sodium chloride crystal would look like, and experiments that we've been able to do on these things over time has shown that that's probably right. They probably really do look like this if we could see them. The properties of ionic compounds are determined by the exact form of that crystal. And here you can see a photo micrograph, a magnified picture of salt crystals, and they're cubical, just like that crystal is cubical. It's because the ions stack together in precisely one way that these look the way they do. Even if the match isn't a perfect match, ionic bonding can still take place. Here's an example, calcium and fluorine. If I look at calcium, I can see that for stability I need to get rid of 2 electrons. Looking over at fluorine, however, I can see that I only need to gain 1 electron for stability. Well, here's what's going to happen. Calcium can lose 1 of its electrons to a fluorine, but it's going to have another fluorine to get rid of the 2nd electron. Well, there won't be just 2 atoms around. There will be lots of atoms, and so it just picks another fluorine and transfers its 2nd electron. Now this does say something about how these things are going to bond. It's going to take twice as much fluorine as it will calcium to form this compound. Well, now you have a 2+ ion and 2 1- ions. So as the crystal forms, you're going to end up with a different form, a different shape, because of the different ratio. And as it grows, you can see that it doesn't look exactly like the crystal that we saw before. In 3D, it wouldn't either. It would have a different kind of a shape. And of course, its properties like color and shape of crystal and its density and other things would be dictated by that arrangement. When we talk about ionic compounds, or any kind of compound, we use something called a chemical formula. The plural is formulae. And the chemical formula gives us two pieces of information. It shows, first of all, what elements are present in the compound, and second of all, it shows what's the ratio of one atom of one element to another. For example, in the two examples that we just saw, sodium with chlorine, we saw that one sodium atom was sufficient to neutralize one chlorine atom. And so we have a 1-to-1 ratio. And these little subscripts here, the 1 there and this 1, tell that story. The same thing is true for the second example, only we needed 2 fluorines for every calcium. And so these subscripts of 1 and 2 tell the ratio, 2 fluorines for every calcium. The chemical formulae show that an ionic compound is neutral. Like, for example, in the calcium and fluorine, calcium made a 2+ ion and fluorine made a 1-. But if you have 2 fluorines, that gives you a total of 2 negatives, and that balances the 2 pluses. With sodium chloride, sodium was 1+, chlorine was 1-. 1+ and 1- balance each other out. Since metals typically make cations and nonmetals typically make anions, we can find that ionic compounds are usually going to form, almost always, between a metal and a nonmetal. So when a metal and a nonmetal make a chemical compound, it's an ionic compound. Let's look at some examples of formulae. With lithium and fluorine, lithium needs to get rid of 1 electron, fluorine needs to gain 1 electron. The match is a 1-to-1. 1 lithium can stabilize 1 fluorine. And so the compound would have LiF. We usually don't write the 1s. Technically, we could write Li1F1, but if the subscript is a 1, we usually just don't write it, so it would be LiF. Here's magnesium and sulfur. Magnesium has 2 electrons to get rid of. Sulfur needs to gain 2 electrons. So magnesium loses both of its electrons to its sulfur, and we see that 1 magnesium is all we need to stabilize 1 sulfur. So again, it's a 1-to-1 ratio, Mg1S1, or just Mgs. Calcium and chlorine. Calcium now needs to lose 2 electrons. Chlorine needs to gain just 1. So calcium can transfer that 1 electron to a chlorine, but it's going to have to get another chlorine, which needs that second electron, to become fully stable. So in this situation, we can see by watching what happened to the dots that 1 calcium can stabilize 2 chlorines. So the formula for this compound is going to be Ca1Cl2, or just CaCl2. You try one. Give the formula for the compound formed by magnesium and oxygen. Write dot notation, follow the arrows, follow where the dots are going to go, and give yourself a formula. Okay, here's your answer. Magnesium is in column 2, that means 2 dots. Oxygen is in column 6, that means 6 dots. So the oxygen is going to need to gain 2 electrons to become stable. And magnesium needs to lose 2 electrons, so the transfer here is perfect. Magnesium becomes a 2+ ion. Oxygen becomes a 2- ion. It takes exactly 1 magnesium for 1 oxygen, so the formula is MgO. Try this one, aluminum with nitrogen. Okay, aluminum is in column 3. That means 3 dots. Nitrogen is in column 5, which means 5 dots. For stability, nitrogen is going to gain 3 electrons. There are the spots for the 3 electrons. Aluminum has to lose 3 electrons, so it'll lose all 3 of its electrons to that 1 nitrogen atom. Aluminum now has lost 3 electrons, so that's a 3+ charge. Nitrogen has gained 3 electrons, so that's a -3. 1 aluminum is all you need for every 1 nitrogen, so the formula is Al1N1, or just ALN. Try this one. Lithium's column 1, that's 1 dot. Nitrogen, column 5, so that's 5 dots. You can see that nitrogen has to gain 3 electrons for stability. Lithium only has 1 electron to give. So lithium can become stable by transferring its 1 electron, but nitrogen can't. It's going to need another electron from another lithium, and then a 3rd electron from a 3rd lithium. Now I have 3 lithium ions that are each 1+ because they lost an electron each, and I've got 1 nitrogen, which is a 3- ion. Since 3 lithiums are needed for every nitrogen, I'm going to end up with this formula, Li3N1, or just Li3N. This one's kind of a challenge. Aluminum and oxygen. Just keep trying until you get it. All right, here's your answer. Aluminum is in column 3, 3 dots. Oxygen, column 6, that's 6 dots. So oxygen needs to gain 2 electrons, but aluminum has 3 to give. Well, the first thing that can happen is aluminum can transfer 2 of its dots to stabilize this oxygen. So now I have an oxygen that's 2- charge. But aluminum still has to get rid of another dot. So I need another oxygen. This oxygen can take 2 electrons, but this aluminum only has 1 to give. So now I need another aluminum. But that aluminum has 3 dots, not 1. It can transfer that 1 dot there, and now I have a stable aluminum that's 3+, and I have 2 stable oxygens that are 2-. Well, I still have to get rid of 2 aluminum, so I need another oxygen. So my third oxygen comes in here, and it needs to take 2 electrons up to become stable. Well, finally we have a match because this aluminum can transfer its remaining 2 electrons into that oxygen, and now I've got 2 stable aluminums that are 3+. I have now 3 stable oxygens that are 2-, and so my ratio is 2 aluminums to 3 oxygens. The formula is Al2O3. There's a shortcut that shows up from the periodic table. And here's how the shortcut works. If you can just remember that group 1s are +1, group 2s are +2, group 3s are +3, like we saw in the last video, and that group 5s are 3-, group 6s are 2-, and group 7s are 1-. So you count up from the left, and then you count down from the right. You can just write down the ions next to one another and then swap their charges. So you write the ions down side by side with the cation first, and then the anion's charge becomes the cation subscript, and the cation's charge become the anion's subscript. Let's look at an example, magnesium bonding with nitrogen. If you look at the periodic table and locate magnesium and nitrogen, you can see that magnesium is located in the second group. Well, magnesium then is a 2+ ion. Nitrogen's in the third group. So I'll write next to it N with a 3- charge. Now here's the idea. I swap these charges. The charge on the anion becomes the subscript on the cation. The charge on the cation will become the subscript on the anion. So Mg3N2 is going to be my formula. I don't have to write dots. I don't have to follow the arrows around to figure out what the formula is. I just write them down. Cation first, anion second, swap their charges and turn them into subscripts. Let's try another one. Barium bonds with oxygen. So here's barium on the left-hand side. It's column 2. That means 2+. So I'll write it down. Ba2+. Group 6 is where oxygen is on the right-hand side, and that's a 2-. So O2-. When I swap these, that 2 goes there, and that 2 goes down there. So I'd end up with Ba2O2. Now for an ionic compound, all you really have here is a ratio of how many ions of each element are there in the crystal. And so it doesn't make sense to have Ba2O2 because all you really want is the lowest whole number ratio. So I'm just going to say Ba1O1 or BaO. So for ionic compounds, the subscript should always be reduced to the lowest possible whole numbers, as we saw there. Practice this. Do calcium bonding with phosphorus. Calcium is column 2, that means 2+. Phosphorus is column 5, and those are 3-. So when I charge swap, calcium gets the 3 for a subscript, phosphorus gets the 2 for a subscript. There's the formula. Aluminum bonding with bromine. Here's your answer. Aluminum's column 3, those make 3+ ions. Bromine is column 7, those make 1- ions. So when I charge swap, aluminum gets the 1, which I don't write. Bromine gets the 3. There's your formula. Try this one, sodium and oxygen. Sodium's column 1, Na1+. Oxygen is column 6, O2-. When I charge swap, sodium gets the 2 from the oxygen's charge. Oxygen gets the 1 from sodium's charge, Na2O. Beryllium with selenium. Beryllium is column 2, 2+. Selenium, column 6, 2-. When I charge swap, I'd get Be2Se2, but remember we only use the lowest whole number subscripts, so BeSe is the formula that I'd use. Anytime you have equal and opposite charges, don't write any subscripts. Last topic for the day is how do we name these compounds? Well, ionic compounds are easy to name if you know the names of the ions. Monatomic, mono means one, so these are one-atomed cations, are called by their element name. So for example, sodium 1+, we would just call it sodium. Or magnesium 2+, we would just call it magnesium, or magnesium ion. Monatomic anion names end in the suffix "ide." So a chlorine ion, Cl-, we wouldn't call that chlorine, we would call it chloride. Or oxygen 2-, we would call it oxide. So to name a compound, you just stick the names of the two ions together and put the cation first. So with sodium chloride, the monatomic sodium ion is just named the same as its element name, sodium. And chlorine, because it's a monatomic anion, is named chloride. So sodium chloride would be the name. Magnesium with chlorine. Magnesium is the cation, so it's just magnesium. And chlorine becomes chloride because it's a monatomic anion, magnesium chloride. Calcium and phosphorus. Calcium is just calcium because it's the cation. And the phosphorus ion is phosphide because it's the anion. Name these three. Well, I think you find this is pretty easy to do. The first one is aluminum oxide. The second one is magnesium oxide. And the third one is barium iodide. Write the formula for these three. Well, this is a little harder than writing the names because you have to think about charge swap. Magnesium's in column 2, so that's a 2+. Bromine is in column 7, so that's 1-. So when I charge swap, MgBr2 is the formula. Strontium sulfide, strontium is in column 2, 2+. Sulfur is in column 6, so sulfide is 2-. Equal and opposite charges mean I just don't have any subscripts at all. Sodium nitride. Sodium is in group 1, so it's 1+. Nitrogen is in group 5, so those are 3-. So when I charge swap this, Na3N is the formula that I have.